All right, I'm back. We're on page 310, and we just learned what a critical point was. So a critical point is a point in the domain of the function at which the derivative is 0 or the derivative is undefined. So now what we're going to do is we're going to use that information and see if we can solve some problems. So find the critical points of x cubed minus 9x squared plus 24x minus 10 and create a sign chart for f prime. So critical points are really important. They're in fact critical when you are making sign charts. So let's start with trying to find our critical points. So first we're going to need a derivative, right? So domain of f of x is all reals because it's polynomial, so we don't need to worry about that. So f prime of x is 3x squared minus 18x plus 24. All right, good start. Hopefully that's right. Now we need to find where f prime is 0 or undefined. F prime is also a polynomial, so it's never not defined. So really we just need where f prime is 0. To find that, I'm going to factor. So I'm going to rewrite it as 3 and then x squared minus 6x plus 8, and then factor that. So first GCF, now factor x and x. You go minus 2, minus 4. Okay, so critical point. So I usually abbreviate that. CP f prime of x equals 0 would give me x equals 2, x equals 4. It's really important to remember that a critical point is an x value. It's not a point on the function. It's a point in the domain of the function. So you don't need to find the y values that are associated with these. And I see a lot of people waste a lot of time trying to do that. So critical points are x values. They're not points on the function. There's often a point on the function where something very interesting happens, but that's not a part of being a critical point. Critical point in the domain of the function at which the derivative is 0 or undefined. So now we got to create a sign chart for this thing. So this would be a trickier question if that positive 3 that we factored out was actually a negative 3, because that would be a negative factor that you'd have to factor in every time you considered if the product was positive or negative, but it's not, it's positive. So sign chart for f prime. And so we're going to put 2 and 4. And I look at f prime and I think it's, so I'm looking at f prime. So how do I show that I'm looking? I'm looking here. That's just a quadratic that opens up. So I know that when I do this, I'm definitely going to get pluses, minuses, and pluses. Like guaranteed that's going to happen because it's quadratic that opens up. If you're not comfortable with that, start picking values, right? So plug in negative a billion. You get positive because of 3 times negative, no, times yes, what am I plugging in? Negative a billion. You get positive because of 3, negative, negative. 2 negatives makes positive. There you go. Plug in 3, you're going to get a positive, a negative, so negative. Plug in 1 billion, positive, positive, positive. So you could do it because of the quadratic that opens up. If you're not comfortable, just test the region. So there's nothing wrong with that. It's just what you like to do. So based on the sign chart, I know that f is increasing, decreasing, increasing. So I actually kind of know that the function looks something like this, where I don't actually know the values, nor am I going to find them, but I know that this is at 2f of 2, and I know that this is at 4f of 4. So I actually know that f of x, so I'm going to write this down. It's not really a part of the problem, but f of x has a relative or local, but relative, maximum at x equals 2. And then why is that? I'm going to say because f prime changes from positive, so POS, to negative at x equals 2. And we could do the same thing for the relative minimum. So f of x. So this justification, you're going to write over and over and over again. So f of x has relative minimum at x equals 4. And why is that? Because f prime changes negative to positive at x equals 4. So if the derivative changes from positive to negative, then there must have been a point where the function went from increasing to decreasing, must have had a maximum. If the derivative goes negative to positive, then the function went decreasing to increasing, there must have been a minimum. So this, you'll find out later, is called the first derivative test for relative maximums and minimums. Relative extrema probably is the right way to say that. But for now, I think we're good with that. Let's move on and take a look at the next question. So given this, create a graph of this thing. Okay, so how do we graph this? All right, we're going to graph it in pieces. So first, what I'm going to do, I'm just going to think about what does x squared minus 16 look like, right? So in fact, I'm going to add that on this graph, but in like a weird color so that we know that it's not like the real thing that we want, right? So maybe in like a light grayish color. So minus 16 is going to be like way down here. So I apologize, that's weird. And then 4, -4. So it'll be, should I go through like real points or should I just kind of like wing it? I kind of want to just wing it. Like at -6, you're already like way up here, I think. So dot this in. So this is before I take the absolute value, and it's before I add 2. Okay, so now if I were going to graph the absolute value of this thing, the only thing that would change is that anywhere this function is negative would reflect over the x-axis. So now the -16 is going to go up to 16. And then all the other parts, so this is like horrifyingly not drawn to scale. All of this will go like this, right? Because all the negatives reflected up. So far, so good. Now what I'm going to do is I'm going to add 2 to every single y value. So, and this will be the real graph, so I'm going to go back to black. So we're going to add 2 to every single y value. So on the y-axis, it's counting by 2. So we're going to have a point here, a point here. This will go up here. Okay, and then good luck with this one. So I don't know, something like that. We're aiming for this, and then I don't know, something. That's not. I think that's not even a function at the end. But that's the basic graph, right? So start with x squared minus 16. Just think about graphing that. Now take every part of that that's negative and reflect it over the x-axis. That creates the absolute value of x squared minus 16. Now take everything and move it up 2 units. That's essentially what we have done. Okay, so can we use this graph to identify the critical points? Sort of. So we can definitively find some critical points. It's possible there are hidden critical points that we can't find. Not in this case, but in general, that's sort of a thing. So you can look at it and you can clearly see where there are going to be critical points. What you maybe can't see is some shadowy ones that have shown up for like weird reasons where there aren't maximums or minimums or whatever. But let's do this. So critical points of f of x. So I look at it and I see, for me, the most obvious ones, for whatever reason, are here and here. So I'm going to say that x equals -4 and x equals 4 are critical points because, so the function is not differentiable at those points. They're relative minimums, so that's like my eye was drawn to those, but they're like sharp relative minimums, which is particularly interesting. So I'm going to say because f prime of -4 and f prime of 4 do not exist, DNE. Okay. Now, is there another critical point? Absolutely. The other critical point occurs here, right, where the function changes from increasing to decreasing, and there's a horizontal tangent line. If we sketch that in, we get a horizontal tangent line there. So I'm going to say that x equals 0 is a critical point because f prime of 0, whoops, f prime of 0 is equal to 0, right? So we actually found 3 critical points, 2 of them because f prime doesn't exist, one of them because f prime is equal to 0. All of them are in the domain, right? So critical point in the domain at which the derivative is 0 or the derivative does not exist. The ones where the derivative is 0 like feel better because it's smooth and people just want curves to be smooth. The ones where f prime doesn't exist are like sharp, kind of weird things, which are actually like a little more interesting. But anyway, I'm gonna stop this here, come back and finish the page in the next video because I don't want this to run too long and I have no idea how long it is. So I will see you in that video to finish the page. See you then.